In the last video, we talked about magnets, what they are, how they behave, and so on. For example, we know that magnets can attract and repel each other. We know that they have two opposite poles that we label north and south. We know that they create magnetic fields, and those magnetic fields can exert forces on other magnets. We use this to learn that we have mislabeled the North Pole, or rather, simply the geographic North Pole is a magnetic South Pole. But we also talked a little bit about the structure of a magnet. By thinking about breaking a magnet into pieces over and over again, we got to the point where we were able to conclude that the atoms that make up a magnet are themselves little tiny magnets, little bar magnets with a north and a south pole. But that's not really a satisfying answer. Where does the magnetism of the atom come from? That's what we're going to talk about today. One of the most straightforward hypotheses we could come up with is that this is somehow caused by charges. After all, magnets behave qualitatively in ways consistent with what we know about positive and negative charges, or at least combinations of them. So maybe, for example, north poles have a bunch of positive charges, and south poles have a bunch of negative charges, or maybe it's the other way around. Well, we can actually test this in a few different ways. The first we're going to talk about is a little thought experiment. Let's imagine that we've broken off one end of the magnet, maybe, for example, the South Pole. Well, now we have a little chunk of material that we used to call the South Pole of a magnet, and our hypothesis is that it was the South Pole because it was negatively charged. Sorry, Pablo's playing with toys if you hear that bird. Anyways, so sorry. So now we're left with just a negatively charged piece of material. This should behave just like a negative charge would. The problem is we learned last time that if I break a magnet in half, I'm left with two halves. Instead of having a south pole by itself, I create a new north pole at one end of it, at the broken end of it. And so if I were to break my magnet in half according to this model, I should be able to separate the north and the south poles. But as we already saw, they can't be separated. Every time you break a magnet in half, you simply generate new north and south poles. So this charge model isn't really working for us in terms of what happens inside the magnet. Now, the second way we're going to prove that this is not the case is actually an experiment that any of you can do at home as long as you can find any kind of magnet. So to prove this, simply take the magnet and try to lift a piece of paper with it. And I don't mean by like putting it under the paper and lifting it up. I mean put a small piece of paper on a table or on a surface and hold a magnet above it, raise the magnet, and see if the paper follows. You'll find that it won't. The magnet is not going to lift the paper unless maybe your magnet is really sticky or something. So how does this prove that magnets aren't electrically charged like this? Well, if you recall, charged objects attract all neutral objects because the charged object will induce a polarization in the neutral object, and that induced polarization will result in a net attraction between the two. So if magnets were charged like this, then bringing a magnet near a neutral light object like a piece of paper would polarize it and then attract it. But magnets don't do that. Now you might say, magnets do sometimes do that. And you're right. Sometimes magnets attract things that are not themselves magnets. But you'll notice that those things are always metals, and that is going to end up being an important distinction. If we had an electroscope, we could also show it that way. We could charge up our electroscope using static electricity and conduction or induction, and then we could see what happened when we bring a magnet near the electroscope. If the magnet itself were charged, it would cause the electroscope to deflect or to sort of undeflect, depending on what charge is closest to the electroscope. But you'll find, and next time you encounter an electroscope, you can test that out yourself. you'll find that there is, again, no deflection. So magnets don't behave the way they do because of some weird charge distribution. The magnetic poles are not concentrations of positive and negative charge. It would be nice and simple to conclude at this point, therefore, that magnetism has got nothing to do with charge. But here is a contraption. This thing on your screen is called a cathode ray tube. So there is a source of electrons in the back here, often called like a bulb, but using a power supply, we can actually knock electrons off of something. And there's a whole bunch of stuff over here. This stuff is actually, right here you can actually see a parallel plate capacitor creating an electric field. But all of this stuff here is really there in order to take the electrons that are knocked off from the source in the back and shoot them out at high speed in a straight line. This blue line here represents actual electrons moving through this tube. The tube is not a vacuum, but it is usually near a vacuum. So it's a very, 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 very sparse gas. And as the electrons move through this gas, they cause the gas to glow. Basically, the electrons on their way they'll knock into some of the atoms floating around in here, and they'll knock electrons off of the atom. And then when the electrons sort of reattach to atoms, they emit light. So this is a cathode ray tube, and it lets us actually see the trajectory that electrons are taking. Note, by the way, these electrons are moving in a straight line. Technically, they're moving in a parabolic arc because they are subject to gravity. You can't tell that it's really parabolic because the electrons are moving so fast that it looks like it's just a straight line. In fact, in a typical cathode ray tube, electrons might be moving at something like 10 to 20% of the speed of light. So they're really moving quite fast. So now let's watch this video and listen to the professor explain what's happening as he brings a magnet near this beam of electrons.
Watch what happens when I bring a magnet near the beam. The beam deflects, which shows that there is a transverse force due to the magnet on the moving electrons. In general, any charged particle that is moving in a magnetic field will experience this fundamental magnetic force. The beam is horizontal outward. When the magnetic field points to the right, the beam bends downward. When we switch the magnetic field, switch the direction of the magnetic field, the beam bends upward. When the magnetic field is pointing straight down, the beam bends to the left. But it has to do that because we can get back to our original case by just rotating the magnetic field. That's where we started from, the beam bending downward. Finally, when the magnetic field and the beam are parallel, there's no deflection. There's no magnetic force.
This is interesting because just a few minutes ago, we showed that charges like electrons aren't affected by magnetic fields. A magnet doesn't cause an electroscope to deflect, which means it doesn't push the charges around inside the electroscope. But here, we have electrons that clearly are being pushed around by an electric field. Or not in this case, but in the other cases when the magnet was pointing perpendicular to the beam. So it seems that in some cases, charges are affected by magnetic fields, and in other cases, they're not. And as you may have already noticed, one of the distinctions that we have here is that in the cathode ray tube, the charges are moving, whereas in a piece of metal or in a piece of paper or something like that, the charges are basically just sitting there, right? They're not going anywhere. So this gives us the beginning of a rule. Magnetic fields can exert forces on moving charges. Now, I said can exert because they don't always exert forces on moving charges, for example, in this case here, and we're going to elaborate on that a little bit more. But if a charge is not moving, then the magnetic field will not exert any force on the charge, as we've already seen in our previous thought experiments. And you may have seen if you actually found a magnet and tried to lift a piece of paper, for example. If you go back and rewatch that demonstration, you'll notice something interesting about the direction of deflection of the beam. It had an interesting property in that the beam was always deflected in a direction perpendicular to both the direction in which the beam is moving, as well as perpendicular to the direction of the electric field applied to it. For example, on the snapshot on the left, the beam is moving sort of like outwards, and the magnetic field is pointing to the right, and the beam is being deflected downwards. So we have three perpendicular directions here: out, to the right, and down. We've actually seen a pattern like this before with torque. You might recall that if you apply a torque to an object, it means you're applying a force at some displacement away from the axis of rotation of the system. And we learned that the direction of the torque on the system is perpendicular to both the force applied to the system as well as to that displacement. And that pattern is represented mathematically by the cross product. So the torque is the cross product of two vectors, r, a displacement, and F, a force. And the result of that cross product is something that is always perpendicular to the two vectors you start with. We also learned that if we don't really care so much about the direction of the torque, but only the magnitude, we can rewrite this as the product of the magnitudes of r times F times the sine of the angle between them. Turns out we can do the same thing for magnetic fields, more or less, and we arrive at an equation for the force on a moving charge in a magnetic field of the form F is equal to the cross product of V, the velocity of the charge, with B, the symbol for the magnetic field. Presumably, this was chosen by someone with a cold or something. I don't know. I can't explain it. We're not done yet, because while our beam of electrons was deflected by the magnetic field, not all moving things are affected by magnetic fields. In particular, it's just moving charges that can be affected by magnetic fields. And so somehow charge has to show up in this equation, and it turns out the bigger the charge is, the more charge that it's moving, or the more charged an object is, the bigger a force it will feel. So instead of F equals V cross B, the equation for the magnetic force on an object, on a charged object that is moving, is equal to Q times V cross B, where Q is the charge of the object, which can be positive or negative. And just like with torque, if all we care about are the magnitudes, then we can express the magnitude of magnetic force on a moving charge as the product of Q times V times B times the sine of the angle between the velocity and the direction of the magnetic field. And remember that Q, V, and B are all magnitudes, so we're talking positive numbers only. In other words, it doesn't matter whether you're going left to right or whether the field is pointing forwards or backwards, or whether or not the charge is positive or negative. This gives us the size of the force, but it doesn't tell us anything about the direction. Now, it is important to note that the direction of the force is different for a positive or a negative charge, because a positive charge would experience a positive number times V cross B, and a negative charge would experience a negative number times V cross B. And that means that a negative charge will experience a force in the opposite direction that a positive charge with the same velocity and the same magnetic field would. In order to get much farther with this, we actually have to introduce some more notation. And that's because magnetic forces are inherently a three-dimensional phenomenon, right? We have V, B, and F. And in general, V, B, and F are, they represent three different dimensions. V and B don't have to be perpendicular to each other, but unless they're pointing in the same direction, they make like a two-dimensional plane between them. And F is perpendicular to those two. And so we have three dimensions that we have to worry about. And that means I want to be able to easily represent that graphically. So the directions that we have are left and right, easy enough. We also have up and down, also not a problem. But then we also have like into the page and out of the page, or away from you and towards you. And I can't draw an arrow in that direction on a flat screen or on a flat piece of paper because it doesn't work. So for towards you, for out of the page, we symbolize that with a by a circle with a dot in the middle. And for away from you or into the page, we use a circle with an X through it. The standard way of remembering which is which, is a little bit morbid. But if you imagine, if you know what an arrow looks like, if you shoot an arrow with a bow, it has the like feathers on the end of it. And if you shoot an arrow and you're watching the arrow recede from behind, you're going to see the sort of cross pattern made by those feathers, the fletching of the arrow. On the other hand, if your friend is shooting an arrow towards you, you're going to see the tip of the arrow coming towards you. And so out of the page or towards you kind of looks like the tip of an arrow. Now, obviously, if your friend is shooting an arrow at you, I don't think they're really your friend, and you should probably end that relationship before things get out of hand. But, you know, who am I to say? I just realized that I forgot to talk about the units of magnetic field. We can see from the equation that the units have to be equal to the units of force divided by the units of charge times velocity. And that gives us kilograms divided by coulombs times a second. We call this a Tesla after the physicist and inventor, Nikola Tesla, who you've probably heard of. There's also another unit for magnetic field strength, which is called a Gauss, after a very famous mathematician / physicist named Gauss. Brilliant, by the way. And a Gauss is a much smaller unit of magnetism. A Tesla is very large. For example, the very powerful magnets in an MRI are usually on the order of like 4 to 8 Tesla. Whereas the magnetic field created by Earth is like 1/10,000th of a Tesla or something like that. So a Tesla is a very, very large unit of magnetic field. A Gauss is kind of a more practical unit, which is 1/10,000th of a Tesla. Let's do a couple examples. And for the first one, let's say that the magnetic field has a strength of 1 Tesla. Let's keep it simple, pointing directly to the right. And a charge of 1 coulomb is moving with a velocity of 1 meter per second, but not directly to the right, 30 degrees away from that. To find the strength of the magnetic force acting on this 1 coulomb of charge, we multiply Q times V times B times the sine of the angle between V and B. And that gives us 1 coulomb times 1 meter per second times 1 Tesla times the sine of, in this case, 30 degrees, which is 1/2. And so the force is equal to 1/2 of a Newton. Now let's do a little bit more of a more complicated example. So let's say that the magnetic field is pointing into the page, so directly away from you, with a magnitude of 1 Tesla still. Let's keep the magnitudes the same. And we have a negative 1 coulomb charge moving, this time let's make it 30 degrees, but to the left instead of to the right. And once again, to find the magnitude of the magnetic force acting on the moving charge in this field, we multiply the magnitudes of Q times V times B times the sine of the angle between V and B. And the magnitudes of Q, V, and B are all +1 with their respective units. And in this case, the angle is 90 degrees because V might be at 30 degrees like from the horizontal, but it is still perpendicular to the direction that is simply away from you, right? In fact, the whole screen you're watching this on is perpendicular to the direction away from you. So V and B are perpendicular to each other, and so the angle between them is 90 degrees. And the sine of 90 degrees is 1. And this time, this charge will experience a force of 1 Newton. Moreover, we can also see that, so the closer to perpendicular that V and B are, the bigger the force on them. Because sine of theta will give us its maximum value when V and B are perpendicular to each other, theta is 90 degrees. And sine of theta will give us the minimum value, 0, when the two are parallel to each other, or anti-parallel to each other, corresponding to 0 degrees or 180 degrees respectively. So a moving charge moving in the same direction or in the opposite direction as a magnetic field will experience no deflection and no force. On the other hand, a charge moving perpendicular to a magnetic field will experience a maximum force. This is a little bit strange. This is the first force we've actually learned about, and in fact, it is really the only force like this, where the force it experiences, the object experiences, depends not on just its properties, but also on its actual motion. We've seen a little bit of this with like friction, right? A stationary object might not experience any friction, but even that's not entirely true because there can be static friction. And ultimately, it's really just a compilation of lots of tiny electric forces causing that kind of behavior. In this case, this is a fundamental force of nature. It's not caused by, anything else. It's a field acting on a charge, and the nature of this force depends on the motion of the charges through the field. This is something we've not seen before, and it makes magnetism actually a little bit more complicated, which is why we're not going to go into quite as much depth with magnetism as we did with electric forces. That covers finding the magnitude of the magnetic force acting on a moving charge. But what if I want to know the direction the force will point, right? In a lot of cases, the magnitude of a force alone is not really very useful. I need to know the direction it's acting as well. Now, because the force is equal to the charge times the cross product of V and B, the direction is going to depend on this cross product. And as we saw with evaluating the directions of cross products with torque and rotation, we're going to use a right-hand rule to do this. So here I've redrawn our first example on a whiteboard. Unfortunately, I don't have the same range of colors of dry erase markers as I do on my computer here. But we have our field pointing to the right, and our charge is moving upwards and to the right. The way to find the direction of the force is as follows. Start by pointing your fingers, your outstretched fingers, so that they're pointing in the same direction as V is. So flatten your hand and point them in the direction of the velocity of the moving charge. The next step is to bend your fingers towards the direction of B. B is pointing to the right, so I need to bend my fingers in this way. Then what you do is you simply outstretch your thumb, and your thumb is the direction of V cross B. So in this case, V cross B is that way, away from the screen, right? If my fingers are this way and I bend them like that, then my thumb points directly away from you. So V cross B is pointing away from us. Now, the force is equal to Q times V cross B. So if Q is positive, then the force is in the same direction as V cross B. So in this case, because Q is plus 1 coulomb, the force is equal to plus 1 coulomb times the magnitude of V cross B in the direction of V cross B. So in the first example, the magnetic force is 1/2 of a Newton, as we found before, and it points into the screen because our right-hand rule again gives us V cross B, and our thumb, which you can't really see very well, right? It points that way. So our thumb points into the screen, and a positive number in that direction is still in that direction, and so the force is 1/2 newtons into the board. We do the same thing for our second example. This time our field is pointing away from us, and our V is pointing up and to the left. So the first thing I do is I start by pointing my fingers in the direction of V, just like before. But I have to turn my fingers so that they're pointing towards B. B is away from us. So in order to do that, I have to turn my hand so that my hand is pointing like this. Note, it's still pointing in the same direction as V. The next thing I do is I bend my fingers towards B, which is away from us. And then my outstretched thumb points in the direction of V cross B. So in this case, V cross B is down and to the left. But remember that the force is QV cross B, and in the second example, Q is -1 coulomb. And so -1 coulomb down into the left direction, the -1 coulomb flips that. I'm multiplying this direction, a number in this direction, times a negative number, and so I flip my hand and I find that the force is going up and to the right instead. So you have to be very careful of to actually include the effect of the charge. Rule of thumb is if you have a positive charge moving through a magnetic field, you just do your right-hand rule. If this were a positive charge, V cross B gives us down and to the left, and a positive charge in that direction gives us a positive force in that direction. On the other hand, when I have a negative charge, I do V cross B. My thumb points down and to the left, but I have a negative charge, so I have to flip it, and so I get it that way. In principle, what you could do is for negative charges, you could use your left hand. This is going to be hard. If I point my left hand in the direction of V, I turn my left hand, and then I bend my fingers in the direction of B, and my thumb points up and to the right, which is the direction of the force. And so you could also use your left hand for negative charges and your right hand for positive charges. There's nothing in principle wrong with that. It's just I've been trained for many, many years to always use my right hand. I'm not really sure which one is better. On the one hand, see what I did there? On the one hand, always using your right hand makes it easy sometimes to forget that you have a negative charge. But if you use your left and right hands, it's easy to accidentally use the wrong hand. So there's no real great way of doing this other than just to be careful about what it is you're doing. Make sure to use the right hand, make sure to account for the sign of your charge. But this is really the rule. Point your fingers in the direction of V, bend your fingers in the direction of B, which may require moving your hand around in different ways. Using the right hand rule sometimes requires kind of contorting yourself in funny ways depending on the configuration of the problem. It's really fun to watch tests where people are using the right hand rule because everyone is sitting there going like, woo, with their hands, and it's fun. All right. Just so we have everything in one place, on the left-hand side, we established that the force was pointing directly into the screen. And on the right, we established that the force is pointing up and to the right. And you can see that in both of these cases, this force is indeed perpendicular to both V and B. But here's the thing. We've established that this magnetic field exerts a force on our moving charges. But if you think back to earlier in the year, if one thing exerts a force on another, then the second has to exert a force on the first. In fact, it has to exert an equal and an opposite force on the first. And so if these moving charges are being affected by a magnetic field, that means they also have to affect the thing creating the magnetic field. So if I shoot moving charges past a magnet, like in the demonstration I showed you earlier, the magnet, through its magnetic field, will deflect, exert a force on the charges. But that means the charges are also exerting a force on the magnet. Well, where is that force coming from? The charges produce electric fields, but the magnet is electrically neutral, and the deflection is in the wrong direction. Electric charges only attract or repel each other, but these magnetic forces do weird things, right? The force experienced by these charges is not in the direction of the field. So it can't be the electric force that's doing this. What's happening here is that it is the motion of charge itself is creating a magnetic field. To demonstrate that, I have another demonstration here, courtesy of YouTube. This has a wire passing through a clear plastic sheet. And if you think about it, what is current if not moving charges? And so in the previous example, we've talked about a single charge moving. This time, let's talk about a whole bunch of charges moving together. Now, this has a few advantages. One is it's easy to make a current. It's hard to make a beam of electrons or even isolate a single electron. And two, it creates a bigger magnetic field, because if one moving charge makes a magnetic field, then a whole bunch of moving charges are going to make a bigger magnetic field. The next step is to pour out a whole bunch of iron filings onto the piece of plastic. And these iron filings, being magnetic, will have a tendency to act like little tiny compasses in the presence of a magnetic field. If you drop these into a magnetic field, they'll tend to align with the magnetic field at their location. So right now there's no current going through this wire, so there is no magnetic field, and the iron filings are all just kind of doing their own thing. So let's see what happens when we turn the current on. now you see that the filings have reoriented themselves into these circular patterns. This is indicating to us that the magnetic field created by this wire is circular. It wraps around like this. And so moving charges produce their own magnetic fields that kind of circle around their velocity vectors. You might have noticed when you watch this that the whole thing was like shaking a little bit. What was happening there is once the current is turned on, not much will typically happen at first because these iron filings are sitting on the plastic, and there's friction. And in the presence of friction, a small force might not be enough to make them kind of slide against the surface. By jiggling or jostling the surface, it breaks static friction, and then the magnetic force will have a tendency to cause the iron filings to settle in a particular direction. This gives us a second right-hand rule. If you want to know the direction of the magnetic field created by a current-carrying wire or a moving charge, you basically point your thumb in the direction of the current and you wrap your fingers around it as if you were holding on to the wire. And then the direction that your fingers wrap is the direction of the magnetic field. Let's do a couple quick examples. So let's say I have a wire like this, and there is an electric current flowing through it in this direction. If I want to know what the magnetic field around this wire looks like, what I do is I take my right hand, I point my thumb in the direction of the current, so up and to the right, and then I curl my fingers around. And it's hard to draw like a 3D diagram. I could draw little rings like this to indicate the magnetic field, but this kind of perspective can be confusing. And so what we usually do instead is we simply draw the direction of the magnetic field on either side of the wire along the plane of the screen. And so if you talk about sort of on the part of the screen above the wire, if you lay your hand out again, according to this right-hand rule, you'll notice that in the portion of the screen above the wire, the magnetic field is kind of pointing towards you. Your fingers curl around towards you on the top, whereas below the wire, they're curling away from you. And so we represent the magnetic field by drawing a field pointing towards us above the wire and away from us below it. One thing to watch out for is if you are actually given the motion of electrons. Conventional current, as I've labeled here, is the direction, it's defined as the direction in which positive charges would be flowing. And so we use our right-hand rule, we get our result, and everything is good. But if I talk about the direction of motion of electrons, for example, my electrons are moving the opposite way, they're moving this way. If I did my right-hand rule with my thumb pointing down into the left in the direction that the electrons are moving, when I curl my fingers around, I'll get the opposite directions as I got here. But that's okay. Now I'm talking about negative charges. And so when I use my right-hand rule, I have to flip the result again. The easiest thing to do is when using right-hand rules to find the field created by a moving charge, always point your thumb in the direction of positive current. So if you have negative charges moving, you want to flip that around first before doing your right-hand rule. In the beginning of this video, I mentioned that we would be investigating the origin of magnetic fields. And we've done that. We've discovered that moving charges create magnetic fields and that moving charges experience forces from magnetic fields. But we started this whole conversation talking about magnets and how when you break a magnet, you end up with a north and a south pole, and if you do that enough, you end up with individual atoms, and that the individual atoms themselves were magnets. So how does this relate to that? The key is in the structure of an atom. Atoms consist of a positively charged nucleus that kind of just sits there and doesn't really do anything exciting. But around that nucleus, you have electrons, and those electrons have some kind of average motion to them. And so the electrons in an atom are moving charges. And it turns out that in some atoms, the electrons as a group move in a way to produce an overall magnetic field. In most atoms, this effect isn't really present, or it's really, really, really small. But in some atoms, predominantly in iron, the effect can actually be quite pronounced. It's also possible to make magnetic materials where the individual atoms are not themselves little magnets, but groups of atoms together exhibit magnetic behaviors for more complicated reasons. But in the end, the origin of all magnetic fields is the motion of electric charges. So magnetism is very closely related to electricity, even more closely, in fact, than what I'm describing here, but it's a little more complicated to get into all the details, because they both are forces that arise as a result of charge, but they occur in different contexts and to different extents, and they have some interesting different properties from each other. Next time, we'll actually investigate this a little bit more. So far, we've only talked about the magnetic fields created by charges moving like in linear patterns. Next time, we'll talk about what happens when you have charges moving in circles, and that is a little bit more related to what we have in an atom. So now you know, where does magnetism come from? It's just moving charges. Whether it's charges in a wire, or the electrons in an atom, or the electrons in billions and billions and billions of atoms together that we call a magnet, in the end, these magnetic fields and therefore forces all arise because there are charges zipping around.